it would be hard to overstate Carver's influence over the last 50 years on the semiconductor world. I mean, Carver, when I was an undergraduate at Caltech, which was, I guess, about 5 years ago. No, actually longer than that. I was an undergrad. When I was a grad student, when I was an undergrad and a grad student, it blends together. Carver was really something of a living legend on campus. He was someone who we all were just unbelievably impressed by what he'd gotten done. And, you know, Carver has done so many things that I'm not even going to attempt to describe all of them. But he did a lot of the fundamental work on metal semiconductor junctions and on the influence of trap states. He did a bunch of the really fundamental basic physics of how semiconductor devices can work and how they can be put together. He invented some of the most important devices. The MESFET was something that he and his group came up with. He did a ton of work on looking at what the fundamental limits of transistors were, and he predicted where we were going to get to in terms of the ultra-small transistors a very, very long time ago. He was actually the person who coined Moore's law. As Matt said, he wrote the key textbook in the field. He was responsible for the creation of MOSIS, which was the original organization that made it possible to do multi-project wafers. He has, if every time you sit down and use your computer or your cell phone, chances are you're using devices that he helped invent or that he helped commercialize. He started something like 20 companies in one way or the other. I know on the list I saw there were 7 or 8 that he was listed as a founder. His students are shot through the highest levels of the semiconductor industry, multiple generations of his students. His companies have developed new technology for cameras on your computer. The trackpads that you use as your mouse are something that he helped develop. He's published 200 papers, 80 patents. His group has just been a powerhouse for decades and decades. He has won pretty much every award you could imagine. And I'm not going to list all of them, but he won the National Medal of Technology. This is a picture of him and the back of our former president. He's won the Lemelson MIT Award, the Kaufman Award, the National Medal of Technology, which I just mentioned, the von Neumann Medal, and many, many others. He is really the grandfather of the field. So without further ado, let me introduce Carver Mead.
Thanks, Michael. The story goes back a little bit before MOSIS, so I thought I would just share a little of that with you. I met Gordon Moore in 1960 when he came by and heard that I was teaching the undergraduate transistor electronics course, and he offered to give me some Fairchild transistors to use in the labs. And of course, I was very thankful for that because I could get a lot better work out of the students if I gave them the transistors than if I asked them to pay for them. So that became a standard technique in getting student projects done. And Gordon asked me to come up and give a talk about my research work up at the newly formed Fairchild organization up in Silicon Valley. And that began a friendship which has lasted to this day. And it started my standard weekly commute to spend my consulting day at Fairchild up in the Bay Area. About once a month, I would invite Gordon and his wife Betty out to dinner, and we'd go to some little place down in Mountain View and have dinner. And in one of those days in 1967, he confided in me that he and Bob Noyce were leaving Fairchild. They had enough disputes with the big corporate bureaucracy back east that they couldn't do it anymore. And they were thinking of starting their own organization. And So I had just been introduced to a brand new computer, we'd call it today. It was a scientific calculator, the 9100 built by Hewlett-Packard. And it was something that sat on your desk, and you didn't have to deal with a computing center, and you didn't have to put up with all that hassle. And it was wonderful. And I spent the evening pitching Gordon that if they were going to start a new company, they should do something that was going to be related to these little things that sat on your desk, because that was going to be an explosive market. So I took Gordon and Betty home after dinner, and Gordon said, why don't you come on in and let me call Bob. So he called Bob, and Bob came over, and we sat in front of the fire and talked about what they might do at this new company. NM Electronics, it was called. Stood for Noyce and Moore. And I did the same pitch with Bob, and we had a long discussion about what that might be. And as a result of that discussion, they asked me if I'd like to consult for the new company, like I'd been consulting for Fairchild. And I can never say no to Gordon, so I ended up working with them to get Intel started. In the beginning, there were 5 of us. There were 4 real employees and this one funny consultant. It was Bob Noyce and Gordon Moore, and then a lady by the name of Jean Jones, who kept everything running. And then Art Rock, who was the first investor, and myself. And then we started hiring people on one thing or another, and it was very interesting to watch this startup company get started. The most interesting thing from the present perspective is the way they did their designs. All the designs were done by drawing schematics on paper and then translating those into layout by someone, a draft person, sitting at a drafting machine and drawing it on Mylar. The Mylar had grid lines on it to guide the layout process. Then, once the layout was on Mylar, it was put on a light table, big light table, which had a thing called a coordinate graph on it. Coordinate graph was a device that allowed you to set very accurately by hand the X and the Y coordinate. The coordinate graph had a thing like a X-Acto knife blade on it. And what you did is you took and you put the layout down, the piece of Mylar, and then you put a thing on top of it called rubylith. How many here know what rubylith is? Yeah, well, I'll have to explain that. It's a clear piece of Mylar with a very thin film on top of it that's red, so that it wouldn't transmit any of the light that's used to make masks with, but you could see through it. So you put that down on the Mylar, and then you use the coordinate graph to trace over the little lines that you'd made in your original design with this X-Acto knife blade until you had one layer transposed from the layout that was underneath into cuts on the rubylith. Of course, if it was a line you were cutting, you had to cut both edges, and if it was a square, you had to cut all 4 sides. Then the rubylith was taken off and put on another light box, and another dutiful worker had the job of taking a pair of tweezers and peeling out the parts which were to become lines on the mask without disturbing the rest of the rubylith. And what you ended up with was a red background with clear lines on it. You then put that up, well, you send it to a mask house. There were mask houses even back then. Send it to the mask house. They did a 250 to 1 reduction, approximately, to get that layout onto a reticle, and then we went right ahead with the process that Michael described. Well, I looked at this, and 2 things happened. One is I had a just enormous felt need to be able to do that myself. Couldn't help it. The other thing was I knew that I mean, I couldn't even afford the light box, let alone the coordinograph, and I couldn't afford the 20 people that it took to do all this. It was crazy. So I had these two reactions. You know, there was this infinite love affair with the technology and this just gut-wrenching thing. How could anybody imagine doing it that way? Well, you know, and how could you ever get it right? It turned out that 90% of the errors were in the process of peeling out the little parts in there because you could hardly see them. It was horrible. So I thought, how am I going to do this? I have to do this. How am I going to do this? So it turned out I was in Southern California, and that used to be a place where a lot of leading-edge aerospace work done. It still is, kind of. And that meant they did a lot of very high-performance circuit boards. Well, it turned out that the layout on a circuit board required about the same kind of precision, percentage-wise, that the layout on an integrated circuit did. So I said, oh, I wonder how they do those. So I nosed around with some of my friends in the aerospace industry, and it turned out there's this thing called a Gerber plotter. And what it does is it takes in a set of commands, digital commands, and it moves a beam of light around on a photosensitive piece of mylar and makes a pattern, and then they develop the whole thing, and now you have an original. Well, I think I could do that. And furthermore, because there are a lot of big aerospace firms that bought a lot of circuit boards, there were job shops around that you could pay by the hour for the time on the Gerber plotter. Well, I thought I'd gone to heaven, so I started studying up on how to write Gerber code. I get pretty good at writing Gerber code. And then somebody at one of these mask houses said, you know, there's this little program which allows you to write, you know, in a real computer language, not just raw Gerber code. What you're doing is writing machine code, and you really should have an assembler to assemble it. So I started writing assembly code to generate these layouts. Well, I don't have to tell you people, it was just what Michael said. Once you can write a program to do something, you're in 7-league boots. You don't need anybody's toolkit. You write your own. I knew what to do. All I had to do was get good at it. There was a little problem seeing what I was doing. It turned out we had one of these god-awful IBM 360 computers, and you had to hand in big decks of cards through a window, and maybe the next day they'd get the results back to you. And I got really good at punching cards. You know, you copy one card onto the other, and then if you want to delete something, you hold this one and punch the new character in, and if you want to, and you do the other thing if you want to insert a character. I don't know how many of you had the thrill of editing punch cards. I got really good at that, and I got pretty good at writing this artwork language, and to see what I did, it turned out that our campus computer had a plotter that was used for scientific data. Well, it didn't care what data it saw, so I would make it, you know, draw the center lines of the lines and the outlines of the contacts, and I know nobody else could look at it, but I could look at it. So I got this going. Well, about then, the students got wind of me doing stuff, and one of the students, Dick Pashley, somebody mentioned him earlier, came around and said, you know, why don't you teach a course in that? We'd like to learn about it. So we started the first course in 1971, and I had already run a couple of chips. It was interesting. I had made the masks and taken them up, and by then we had some former students that were in the Intel fabs, and so I'd give them the lot, and they would run it through as an engineering lot. And I stopped in to see Gordon and Bob and said, you know, I'm running a lot through your line as an engineering lot. And they said, oh, I think we'd rather not know about that. And that began a very nice process where, of course, more and more of these students who learned how to do this would move up to Intel, and so they would help the process along. So every year we would run a class, and each of the students would do their own little project. And because I had a computer language, they would write their little project, and then I would make that an element in the whole project chip, and then I would write one little thing that said where to place each of the student projects on the reticle, and then we would make one reticle with all the projects on it, including the bonding pads and everything. We'd run it, then when it would come back, each student would go in and carefully bond out just their project. Some were better at bonding than others. And we'd get their projects to work, and it was just like real thing. Well, then, of course, what happened is those students started going out and doing more things, and they'd get hired someplace. They didn't all get hired by Intel, Justin. And they'd encounter, just like that clock thing you saw, they'd encounter a problem and say, oh, we know how to do that. And their boss would say, you can't do that. And they said, hey, we did something more complicated than that when we were an undergrad. And they'd say, oh. And so that was what was going on. Okay, so we did this for a while, and that brought us through the 70s and lots of details. But in 1979, 3 or 4 really important things happened. One was that I'd been working with Lynn Conway to get this book done that you saw, and we had a draft, not a draft, we had a version we could print one off in 1979. And the people right here at the UW offered to put on a teacher's course, because by then a lot of other universities had heard about this stuff and wanted to teach it. And so the UW hosted an all summer long, turned out for me it was all summer long. Most people took their vacation and came to this course and worked around the clock and did a design and learned how to do this stuff, and then went back to the universities and started teaching it. And then when I got back to Caltech, we had the Caltech VLSI conference, and 2 important things happened there. One was that Dave Johansen gave his first talk on his silicon compiler that he made, which was the first more or less general purpose silicon compiler. And I gave the first talk on silicon foundries and people that wanted to design chips but weren't going to fab them themselves, and how that could be a business model. We didn't have the term fabless at the time. Just said this would become an important part of the semiconductor industry. Well, the combination of those courses going out there and the fact that they wanted chips fabbed meant that we needed a good, reliable source of supply. Meanwhile, the fact that I was talking about the fabless semiconductor model got a number of people at Intel rather upset with me. So they weren't as willing to be supportive of the fab process as they had been before. And they got friendly later on when they realized that we hadn't really taken their market share away or anything like that. But there was a period where it felt like a zero-sum game. It wasn't. It was a very positive-sum game, and that was the whole point of it. And that's the point of OpSIS, that what you're going to get is so much creativity, just like we got with the MOSIS project. Well, you mentioned MOSIS, so I'll mention it. Ivan Sutherland had joined us in 1975 and helped get a program going there, where VLSI and computer graphics were the 2 centers of what we were doing. And he had been a DARPA director, and he knew the DARPA people. It was probably ARPA then, not DARPA, but anyway. So he convinced DARPA to support this MOSIS facility. And we got a very smart guy who had been one of our early students, a guy by the name of George Lewicki, to direct the MOSIS facility. And you wanted to know where the name came from. We had a wordplay fellow. MOSIS got housed over at a place called ISI, which was a little lab run by USC. and it was over in Marina del Rey, and there was a guy there by the name of Danny Cohen, who was one of these wordplay type people. And he decided that it should be MOSIS, because it would lead everybody out of the wilderness. And so that's how the name came about. So one thing led to another. I spent about the next 6 or 8 years going around to all the semiconductor companies that I could get an audience with and trying to convince them that being a foundry was really, really a good business opportunity. And this involved going all over the United States. It involved a trip to Taiwan in 1980. And most of them nodded and smiled and said, yes, we understand how that can be interesting business, but we'd like to own the design when we're done. And I would try to explain to them that that was not going to be a sustainable thing and so forth. So on we go. You all know that finally, in 1987, Morris Chang, well, actually, the government of Taiwan had kind of listened when I was there, and things had bubbled up through it, and eventually that got turned into TSMC, and now it's responsible for a lot of the value created in the industry of electronics. That's what can happen if you start little like that. But you give people the ability to write their own code so they're not at the mercy of somebody that already decided how it's going to be done, because that doesn't work. It works because people see a new way that it hasn't been done, and they're perfectly happy to write their own code. And as long as you can do it by writing code and building your masks that way and building your test vectors that way, you'll be fine. If you try to dictate what people are going to do with it, they'll go around someplace else. So I think there's every bit as big an opportunity here as there was when we started out. Remember, it starts really small. Remember, I told you, first course we taught at Caltech, first multi-project chip, 1969-70 academic year. It was almost 20 years before TSMC became the major supplier of foundry services. So I have only one last thing to tell you, and that is, you know where the term silicon foundry was coined? Anybody know? Anybody know? Most people think I did it. I didn't. Intel had a fab in the on Bowers Avenue. That was the second fab. The first one was on was down on Middlefield. That was the one I knew really well. Then the one on Bowers Avenue, and the third one they put up was in Livermore. And I would go over there to visit Ted Jenkins, who had been a former student, and he would sneak the lots through the line for me. And I would take he and his guys out to dinner, and, you know, it was a mutual back scratch. And I was talking to Gordon about the Livermore fab. And that was just after Intel had introduced the 1103, which was the first dynamic RAM chip that ran in volume. There's another story about that. And he said, oh yeah, Livermore, that's going to be become just a foundry for stamping out 1103s. So it was Gordon Moore that coined the term silicon foundry.